one broken link, 380 pounds of steel, 30 hours to fix it, or Starship doesn't fly. Right after static fire, the entire tower shook. A loud bang. The chopstick arm's massive chain had snapped. No spare chain on site. Crews flew one in overnight from the Cape, 400 miles away. They tore the old chain apart, rebuilt it by hand, installed it before dawn. This is the real story behind Flight 12's final countdown. Stay with us. The static fire test had just ended. 10 engines, full duration. A milestone SpaceX had failed to hit 3 times before. The team should have been celebrating. Instead, they heard a bang. The chopstick arms were lowering back into position. Routine. Or it should have been. Then came a loud noise, loud enough to vibrate the entire tower. Engineers on the ground felt it before they understood it. Something inside the chain had failed. Not a small chain. Picture a bicycle chain scaled up to industrial size, 380 pounds per link section, built to carry a carriage that weighs more than a loaded semi-truck. That chain had just jammed, or snapped. Nobody knew which. Not yet. And here's the number that mattered most. Launch was 2 days away. Why? This chain breaking was never supposed to happen. To understand why this moment mattered, you have to understand what the chopstick arms actually do. They're not decorative. They're not just for catching boosters. They are the mechanical spine of the entire launch tower. They lift Starship. They stack it. They catch the booster on return. If the chain fails, the tower can't move the rocket at all. SpaceX calls this whole structure Stage 0, not Stage 1. Stage 0. Because without it, there is no Stage 1. There is no launch. The pad itself is treated as part of the rocket. So when a component inside that system breaks, it isn't a minor maintenance issue. It's a program halting problem. Here's the twist most people don't know. This component wasn't even designed to be easily serviceable. It wasn't built with a quick swap in mind, which meant the team wasn't just fixing a broken part. They were improvising a repair procedure that didn't officially exist yet. So what do you do when the part that breaks was never meant to be replaced quickly? This is where the story gets interesting. SpaceX didn't have a backup chain sitting at Starbase, but they had something almost as good, a sister site. Cape Canaveral, roughly 400 miles away, had spare units left over from building their own towers. One call, one overnight flight. The chain was in Texas before sunrise. Then came the real work, tearing apart the damaged chain, rebuilding a replacement by hand, link by link, each section weighing 380 pounds. Lifting the carriage, it powers back into position using cranes that weren't originally part of the plan. All of it improvised on the spot. Total time from discovering the problem to having the tower fully back in service. About 30 to 36 hours. Think about that number for a second. A component that wasn't designed to be serviced quickly got diagnosed, sourced, rebuilt, and reinstalled in under a day and a half. That's not luck. That's a team that has built the muscle memory for exactly this kind of crisis. But fixing the chain only solved one problem. A much stranger one was still waiting at T-minus 40 seconds. The first abort, a problem nobody simulated. Launch day arrived, countdown proceeding normally, then holding at T-minus 40 seconds. The issue wasn't the chain. It wasn't the engines. It was something almost nobody outside SpaceX had ever heard of. The ship's quick disconnect arm, known as the QD arm. Here's what it does in plain terms. Right before liftoff, this arm has to unpin itself so it can safely swing away as the rocket leaves the pad. If it doesn't unpin correctly, the rocket can't launch. During this attempt, engineers unpinned the arm for the very first time under real flight conditions, and something unexpected happened. As the pin released, the arm pushed harder against the tower than expected, causing it to shift slightly, just a jiggle. That tiny movement triggered ultra-sensitive pressure sensors in the hydraulic system. The system read the jiggle as a fault, and it stopped the countdown. Here's the part that should genuinely surprise you. Engineers going into this launch were worried about a completely different risk, unrelated vent pressure during propellant loading. That risk passed without issue. Then a completely unrelated system, one nobody was watching closely, caused the abort instead. This is the reality of rocket engineering that rarely makes it into headlines. You can prepare for the danger you expect and still get ambushed by the danger you didn't. So the team scrubbed the attempt, rolled back, regrouped, and went looking for answers. The next day, they tried again. This time, engineers had a plan: clear the hold, let the arm attempt to unpin one more time at the same hydraulic pressure. One shot. If it didn't work, the launch attempt was over for the day. They released the hold, and the arm failed to unpin again. But here's the twist that separates good engineers from great ones. The second failure wasn't the same failure as the first. Engineers immediately recognized a completely different pressure drop signature this time, something in the Z cylinder blind pressure that hadn't shown up before. Different symptom, different root cause. Same result, no launch. At that point, the flight director made the call nobody wants to make after this much preparation: stand down for the day. Trying again wouldn't fix a problem they didn't fully understand yet. That's a hard decision to respect, because the easy thing to do, the thing that feels good in the moment, is to push forward and hope. SpaceX didn't do that, and that decision is the difference between a scrub and a disaster. So what actually was going wrong with this arm, and could they fix it before the next attempt slipped away entirely? The fix. Nobody sees in the highlight reel. Overnight, engineers traced the root cause. The QD arm's cut mechanism was pushing a preload force into the vehicle. When the pin released, that stored force created just enough dynamic movement to trip the hydraulic sensors, twice in two different ways. The fix wasn't glamorous. It was a welded, hard-stop bumper, added directly to the ship's QD arm. Its entire job: physically limit how far that arm could shift when the pin released. No fancy new software, no redesign, just a precisely placed piece of metal built to absorb the exact motion that had aborted 2 launch attempts. This is what real aerospace engineering actually looks like. Not always dramatic breakthroughs. Sometimes it's identifying 6 inches of unwanted movement and welding a stop into place before the next countdown. The next morning, flight directors confirmed the mitigation was in place. Range clear. Weather green. Every team, one by one, called out, go. Would a single welded bumper be enough to solve a problem 2 full launch attempts couldn't get past? Before we get to launch, it's worth understanding just how much force this pad is designed to survive, because it puts everything you just read into perspective. Starship's engines produce about 18 million pounds of thrust, numbers that large stop meaning anything on their own, so here's a comparison that actually lands. 65,000 pounds of propellant leave the engines every single second. That's roughly equivalent to 11 full-size pickup trucks being fired out the bottom of the rocket, every second continuously for the entire ascent. Now picture what that does to the ground underneath it. To survive that, SpaceX built a flame deflector system that pushes around 650,000 gallons of water per minute across the pad, roughly an entire Olympic swimming pool drained every 60 seconds. The water isn't there to cool the rocket. It's there to absorb an amount of thermal energy that would otherwise melt structural steel in seconds. Engineers actually track heat levels using metal sensors chosen specifically because of their melting points: aluminum, zinc, copper, and even something as simple as a permanent marker. If the marker survives, the system is doing its job. This is the same pad, the same tower, the same mechanical systems that had just failed twice due to a small metal arm shifting a few inches. That's the contradiction at the heart of this program. Systems built to survive nearly unimaginable violence can still be undone by a component small enough to hold in one hand. That contradiction is exactly why every abort matters, and exactly why this pad was also carrying something extraordinary on board for this flight, something that had never flown before. The heaviest cargo SpaceX has ever launched. While engineers were fighting through aborts on the pad, another story was unfolding inside Starbase's factory floor: the payload. This flight carried 22 total objects. 2 of them were real, functioning satellites, complete with laser optics for satellite-to-satellite communication and onboard thrusters for maneuvering. The other 20 were satellite simulators, solid steel objects shaped and weighted to mimic real satellites, built purely to test how the deployment system, nicknamed the PEZ dispenser, handles rapid, repeated releases. Combined weight of all 22 objects, roughly 3,712 metric tons. That number deserves a second look, because it's heavier than any payload ever launched by a Falcon rocket, and by the team's own account on the day, likely the heaviest payload SpaceX has ever sent to space. Here's the added context most coverage of this flight leaves out. Testing a deployment mechanism with dummy mass isn't just about proving the hardware works once. It's about proving repeatability, 22 separate release events, back-to-back, under real flight vibration and thermal stress. 1 clean satellite deployment proves the system can work. 22 proves it can be trusted for an actual operational constellation. That's the quiet, unglamorous kind of milestone that doesn't trend on social media, but it's arguably more important to the program's future than the launch itself. So the rocket had to survive 2 ground aborts, a broken tower chain, and a QD arm with 2 different failure modes, all before it could even prove this payload system worked. Which raises the obvious question. After all of that, would liftoff finally happen? While the ground team fought through the pad's problems, an entirely separate operation was already underway, one most viewers never even think about. Roughly 500 nautical miles offshore in the Indian Ocean, a recovery ship had already been sailing for 2.5 days. Its mission? Deploy buoys equipped with cameras to capture Starship's re-entry and landing, specifically its heat shield. These buoys aren't new. They trace back to Flight 5, when they were deployed as what the team itself calls a Hail Mary attempt, thrown together quickly without much confidence they'd even work. They did, and every flight since, they've been refined, patched, and redeployed. For Flight 12, this was, by the recovery team's own account, the most extensive version of that operation yet. The most buoys, the most drones, the most cameras they had ever positioned for a single re-entry. Why does this matter so much? Because a rocket that reaches orbit but burns up unpredictably on the way down isn't reusable. The entire economic model behind Starship depends on the heat shield surviving re-entry reliably, flight after flight. Without visual and sensor data from that descent, SpaceX is flying blind on the exact system that determines whether this rocket can ever be reused on a fast turnaround. So while cameras on land were capturing the drama of the countdown, cameras in the middle of the ocean were quietly preparing to capture the answer to a much bigger question. Is this heat shield actually ready for repeated flight? Ignition, 5 out of 6. Countdown resumed. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition, liftoff. The vehicle pitched downrange, pushed through max Q, the point of maximum aerodynamic stress, and reached stage separation. Then, almost immediately, a new complication. Flight controllers began acknowledging multiple booster alerts. Engineers confirmed an early boost-back shutdown was expected. Moments later came the harder confirmation. The booster did not make it to its final landing location. Let that sink in for a second. After 2 scrubbed attempts, a broken chain, a welded emergency fix, and the flight's record-setting payload, the booster, the first stage, the part designed to come back and be caught, was lost. But the story wasn't over, because the ship itself kept flying. Engineers confirmed something critical. The ship's avionics, power, and telemetry were all reading nominal, and chamber pressures were healthy on 5 out of 6 ship Raptor engines. 5 out of 6, not all 6. One engine was already showing problems, and the ship was still committed to completing its mission on the remaining 5. This is where the story shifts from pure danger to something closer to redemption. Despite everything that had gone wrong before liftoff, despite an engine underperforming mid-flight, Starship continued its trajectory, turned for final approach, and began its descent toward the landing zone. The same zone being watched by every buoy and drone stationed hundreds of miles out at sea. And then, the words the entire team had been fighting 2 days of aborts, a snapped chain, and a lost booster to hear: Starship has landed. The reaction in the room wasn't scripted celebration. It was the sound of people who had just watched a program survive its own most dangerous week. Engineers repeating the same word over and over: heat, heat, watching thermal camera footage of a vehicle that had just proven, in front of the most extensive ocean recovery operation SpaceX has ever run, that its heat shield could take the punishment of re-entry. What this flight actually proved. Here's where it's worth stepping back and adding something the raw footage alone doesn't tell you. This wasn't a clean, one-take success story. It was a flight that survived a structural failure on the ground, 2 separate and distinct abort conditions on the same mechanical system, and the loss of an entire booster stage, and still delivered a successful ship landing with the heaviest payload of the program to date. Compare that to how most people imagine spaceflight: flawless countdowns, perfect engines, nothing going wrong. That image has never matched reality, not for SpaceX, not for NASA, not for any program that has ever put something this large into the sky. What actually separates a functioning space program from a failed one isn't the absence of problems. It's how fast the team can diagnose an unfamiliar failure, engineer a fix overnight, and decide correctly when to hold and when to go. 2 failures on the QD arm, 2 different root causes, 1 welded fix that worked. A snapped chain repaired in a day and a half using improvised cranes and a favor from a sister facility 400 miles away. A booster lost, and a ship that still stuck the landing on 5 working engines while carrying more weight than any SpaceX flight before it. That's not a story about a rocket. That's a story about an organization's tolerance for chaos and its refusal to let chaos turn into catastrophe. The booster didn't make it back this time. But the data from everything that went wrong, the chain, the arm, the engine, is now sitting in the hands of the same engineers who welded a bumper into place overnight and got a rocket off the ground less than 48 hours later. Which raises the real question hanging over the entire program now. If this is what SpaceX can recover from in under 2 days, what does that mean for how fast Starship is actually going to keep flying? Every abort, every fix, is the real engineering story. Thanks for breaking it down with us. Like, share, comment your take, and subscribe to the Space Brief. More analysis is waiting on screen.